Hi everyone. Sound is good? Okay. Glad to be able to introduce my work here. I will talk about part of my PhD work that I'm doing at University of Bern with Katarina Wilmes, who is just right there, and Walter Zen and Mihai Petrovici. And so what we are interested about is predictive coding, as nicely introduced by Rafael Bocage, and also taking into account uncertainty in models of cortical function, of cortical computation. And these two areas meet when we try to model the variance of cortical predictions. So in the predictive coding literature in general, the variance of cortical predictions are written as parameters of the model to be averaged across all experiences, but rather we argue that we should write it as a function of current activity, so dynamically estimated and context-dependent. And this echoes some ideas already present in the predictive coding literature, but we found this has never been formalized. And to formalize it simply means writing cortical predictions as Gaussian distributions, where both the mean and the variance are written as function of current activity, of current representation. In other words, what this means is that cortical areas, they don't only send predictions about the activity vector in other areas, but my bad. So my first slide was too long. Okay. So cortical areas don't only send predictions about the activity vector in other areas, but alongside these predictions, they also send confidence signals about how confident they are in their prediction, where we define confidence as the inverse expected variance. And for those interested in differential geometry, these confidence signals actually act as metrics on the error landscape. And so when doing this, having this natural extension of predictive coding with the variance as a function of current activity, and following the classical derivation of predictive coding dynamics, we see two things. The first thing will not surprise people who do Bayesian statistics, because it simply says that prediction errors should be weighted by confidence signals. And so this leads to Bayesian optimal estimation in neural dynamics, even in dynamically varying environments. And this could be seen as a model of inhibition and disinhibition in cortical circuits, particularly of the zone between the apical dendrite and the soma of pyramidal cells, where the integration between bottom-up signals and top-down signals occur. And we map this quite precisely to interneuron circuits based on experimental evidence. I don't have time to present the details, but you can come and talk to me if you want. That's the first thing that we see with this very natural extension of predictive coding. And the second thing is that when you do the math, do the derivation, you see the appearance of second-order errors or confidence errors, which are simply encoding the difference between how confident an area is and how well it actually can predict things. And so this is, let's say, a very high-level experimental prediction that we can do with this natural extension of predictive coding theories. And these errors, so first of all, they are linked to risk prediction errors in the reinforcement learning literature. So it's like the link between reward prediction errors and prediction errors in predictive coding. And they are used to learn how to estimate confidence through a local synaptic learning rule that is also derived from first principles. And they are also used in neuronal dynamics. They are propagated through the cortical hierarchy alongside the classical prediction errors. And they lead to very interesting new computational capabilities, like the ability to perform nonlinear classification in a single layer. So the bottom line is, and this is the last slide, the bottom line is, if you have models, mechanistic models or normative models that use Gaussian distributions, maybe you could try writing your covariance as a function of current activity. This could lead to very natural and principled extension of your models that capture more phenomenon. And some more discussion points. So the main one maybe for this conference is that these confidence signals, they are multiplicative attention masks that are dynamically computed at every time step. So this may ring some bell for the transformers people. Maybe there is a link between attention in predictive coding, in the predictive coding literature, and attention as it is construed in machine learning right now. And one last sentence. What I'm super interested in right now is the idea of modeling attention as an adaptive metric on the error landscape during neural dynamics. So if you're interested in this, and you like differential geometry, I'm quite interested in talking. And that's it for me. Thank you.